Okay, so yeah, as Ralph just said, I'm going to talk about some work I've been doing over the last few years with a group in Hamburg. So that's Jan Louis, Christoph Horst, Hagen Trindle, and mathematician Vicente Cortez, and also a guy in Indonesia, Bobby Ganara. So why n equals 2 supersymmetry? I'd like to give a few rough words of motivation. Just it's probably not necessary at all for this audience, but let's see. So compactifications of string theory obviously often lead to n equals 2 supergravity in 4 dimensions, with many massless scalar fields or moduli. N equals 2 supersymmetric field theories are very constrained, with many relations between the various couplings, which make them easier to study. But of course, there's no chiral fermions, which means phenomenologically they're maybe not so interesting, you would think. However, it turns out that various phenomenologists over the years have studied the idea that perhaps the standard model, or the MSSM, has a further extension in the gauge sector, which has extended supersymmetry. And this actually has very different signals compared to the MSSM. And another option is that you could look at n equals 2 Dirac fermions, or the mirror fermion partners to our regular fermions, as being dark matter candidates. And this has been studied by various people, and in fact people have been looking at things even for the LHC for this. So a general overall question one could ask then is, can n equals 2 supersymmetry be spontaneously broken to n equals 1, perhaps in some visible sector, in a way in which you can realize a low energy chiral spectrum? This is obviously quite a difficult problem. It's perhaps not possible. But what we've done to begin with is try to have a systematic study of spontaneous supersymmetry breaking in supergravity. So why did we have to study it? Well, it turns out that long ago now, there was a famous no-go theorem which said that for a very large class of supergravity theories, you couldn't break n equals 2 to n equals 1 supersymmetry. This is the title of the paper by Ciccotti, Girardello, and Parati. But of course, what happened, like with all good no-go theorems, sometime later, some counterexamples were found. So using some very special choices of matter content in n equals 2 supergravity, Ferrara and collaborators found a way around this no-go theorem. So what did we do then? Well, it's all about this special choices here. We used a new formalism that was introduced in supergravity called the embedding tensor formalism to show that in fact one can find an n equals 1 vacuum in any abelian n equals 2 supergravity with 2 commuting isometries. Furthermore, we just very recently looked at whether one could realize n equals 2 and n equals 1 vacuum inside the Kähler cone in a given supergravity, and we found the answer was yes, but you have to check case by case. So what I want to do in the rest of the little talk today is just explain a little bit more about this result. And in particular, I want to explain about the utility of the embedding tensor formalism, because it seems a bit unusual to a lot of people, and so I hope I can at least motivate why it's useful to use. So the embedding tensor formalism was introduced by DeWitt and collaborators some time ago now, and essentially the embedding tensor itself is just a matrix of charges. It's taken to be spurionic, so you set this guy up to begin with and you allow it to transform such that you can reinstate various dualities in the theory, and then at the end you fix it to a constant value. So basically what this matrix does is it selects the subset of your global symmetry generators that are going to be gauged in your gauge theory. So here they are, these are going to be the guys that you gauge, and these are the global ones over here, and this matrix just selects what's what. This can handle, this formalism can handle electric and magnetic charges, and a gauging in general then you'll write down in this way. So you have some scalar field over here, and under a gauge transformation you now say it goes like some parameter, these matrices themselves, and then just some killing vectors in your sigma model, for instance. And then covariant derivatives, they're simply defined like this. So everywhere before you just have you had a gauge field, you can now just throw in this extra guy and the killing vectors. But of course, if you have electric and magnetic charges around, you have to be careful. And what one does is you enforce an additional constraint called mutual locality, which makes sure you can always rotate back to a frame where you only have electric charges and everything makes sense, all your physics makes sense. So this is all fine, but how can we actually use this formalism to do something interesting with the physics in the end? And so this is the main thing I want to convey today on this slide. The advantage of the embedding tensor formalism is that one can leave the matter content of your supergravity theory general. You want to fix then the physical characteristics that you're interested in, so some physics that you want to find, and then you go about solving for the gaugings and the charges in terms of this embedding tensor that will allow you to find that physics. So in some sense what you do is you fix the physics and then you're able to solve for the theory that you want afterwards. So it's a bit of a flip around to what we usually do. Usually we take a supergravity, fix the charges and say, oh, does this have black holes? Does this have partial supersymmetry breaking? Does it have some interest in solutions? But this is something else. This is really that we say we want to find some particular physics and we want to know which theories will allow us to have that. And this is really all possible because of this interest in formalism where this guy's spurionic and it allows for a very general setup. So here's the application, and this is what we did over a series of papers over the last, like the last 4 years now. So to find an n=1 supersymmetric vacuum of an n=2 supergravity, we can simply solve the Killing-Spinner equations. So these are the guys that follow from the supersymmetry transformations. Now, obviously, in general, these are quite complicated. I don't want to write them all down in the slides for you, so I'm going to have cartoon equations here. So, nevertheless, for a Minkowski vacuum, if we want to find a Minkowski n=1 supersymmetric vacuum, these Killing-Spinner equations simplify to just the scalar parts. So we have some matrix here, which you can write in terms of the embedding tensor itself, so basically just the charges. The scalar fields in your theory, which I'll call Q's, and the isometries on the sigma model, the K's. And so then for all maximally symmetric spaces, actually, the supersymmetry transformation is reduced to something very simple like this. Now, if we want to find an n=1 vacuum, we need to find a particular solution to the equations which follow from this. So an n=1 vacuum is found like this. You have, for n=2, for instance, which I'm interested in here, you have one of these scalar matrices coming from the Killing-Spinner equation, and it has the equation to 0 like this. So you have to solve one of these guys to 0, and that tells you that you have one unbroken supersymmetry. But importantly, you have to break the other supersymmetry. So you need to find some solution for these S matrices, which allow this equation to vanish, and this equation to be non-zero. So at this point, it's worth reminding what the 1984 no-go theorem did. It basically showed that in n=2 supergravity for a very large class of theories, all the matrices of interest in any fermionic variation like this, so this can be any fermion in your theory at all of these matrices were basically proportional to the identity matrix, which means that you can never have this situation where one of these guys vanishes and the other doesn't. So what we did then is simply solve these equations for these scalar mass matrices that appear here. These guys essentially are the mass matrices of the fermions. And we solved them for the embedding tensor components themselves, given in terms of the the scalars and the Killing vectors and the pre-potential of n=2 supergravity. We solved these guys at some point, the n=1 point. So afterwards, this guy is no longer, it's no longer a matrix of things that can transform. It's really a set of constants, and that's why it's important that you fix everything at the n=1 point. So basically then what we found is that we could solve for the charges and the gaugings in this n=2 supergravity, and we could find all the charges and gaugings which would give rise to n=1 vacuums. So in some sense we found the space of theories which will allow you to have partial spontaneous supersymmetry breaking. So it turns out that these solutions actually had some interesting properties. So in particular, the solutions themselves, so these embedding tensor components are really just the charges of the theory. They're given entirely in terms of the Killing vectors, K, and the pre-potential in the n=2 theory. And the n=1 condition can be solved if there's two commuted isometries. That's the only condition we had, really. So some properties of this is that it turns out that there's no constraint on the vector multiplets whatsoever. It turns out that everything was protected from quantum corrections, so we looked at the various instanton corrections too that one can consider, and this didn't change the result. Interestingly, if we tried to find a string interpretation for this set of charges within n=2 supergravity, we found out it was given by precisely the kind of non-geometric fluxes that the guys were talking about in the last two talks. So this is pretty interesting. We also we extended our result, which was on on some general grounds for quaternionic Kähler manifolds. We extended this to all the quaternionic Kähler manifolds that are in the C-map. So these are the ones that come from string compactifications. And as I mentioned already, both n equals 1 and n equals 2 vacua can exist inside the same Kähler cone in one of these theories, which is also nice to see. We find some further surprises along the way. So having found the various n equals 1 vacua of n equals 2 supergravity, thanks. We then decided to look at the low energy effective theories in these vacua. So what we had before were all the charges which in field space would give us the points where we have n equals 1 and not n equals 2 supersymmetry. So now you can go to one of these points and you can study the low energy effective theory in that vacuum and you can see what you find. Now, obviously the first thing you find is n equals 1 supergravity because that's the amount of supersymmetry you have. But then it turns out that because we have n equals 1 coming from n equals 2, it turns out that there's an additional constraint which enforces a very large number of the massless scalar fields to become massive. So this is really the four-dimensional version of moduli stabilization. And this comes for free when you spontaneously break supersymmetry from n equals 2 to n equals 1. So for instance, if you have cubic prepotentials in your n equals 2 theory, then all the vector multiplet scalars get fixed. And a little more than half of all the hypermultiplet scalars get fixed for free. And that's pretty neat. So when we were working out this low energy effective theory, it also led us to a new construction of Kähler quotients of quaternionic Kähler manifolds. This was interesting for the mathematicians in Hamburg because previously Kähler manifolds were constructed as submanifolds of quaternionic Kähler manifolds, and there was a strong bound on their dimension, and this new quotient construction allows you to have a far larger dimension for the Kähler quotient. We also found out along the way that all the quaternionic Kähler manifolds in the C-map have a natural global complex structure, which is pretty interesting. So furthermore, what we've been doing recently is seeing how you can extend these various results to rigid spontaneous partial supersymmetry breaking. And that's interesting, but there's some trickiness when you try and match the two theories together, looking at the global limit. And very recently, we used the same techniques that we used here for partial breaking, just to look for n equals 2 supersymmetric ADS vacua in n equals 2 supergravity. So this has been a big topic over the years. And we find a quite surprising result, we think. We find that in n equals 2 supergravity, in 4, 5, and 6 dimensions, there are no n equals 2 ADS vacua which come from SU3 times SU3 structure compactifications of type 2 string theory and M theory. So this is quite surprising, we think, and this is because of the kind of symmetries which appear from these compactifications. So this brings me to my conclusions. All I really wanted to convince you of today is that the embedding tensor formalism has useful applications beyond constructing the most general supergravities that you might be interested in. It actually has applications when you want to study particular physical properties of those theories too. And I hope I convinced you that what you're able to do with this formalism is choose the interesting physics that you want to find in your class of theories, and then you solve for these embedding tensor components, i.e. charges and gaugings, which will allow you to have this physics. So our application was to study n equals 2 to n equals 1 spontaneous supersymmetry breaking in supergravity. And we find that it's completely fine and robust. Generally, you can find it, whereas before it was thought that very special choices were required for the matter content. We find that the n equals 1 low energy effective theory is not generic, and that many massless scalars become massive. So there's moduli stabilization, which goes for free in n equals 2 supergravity when you look at spontaneous supersymmetry breaking to n equals 1. I also mentioned that we find some new construction of Kähler quotients of quaternionic Kähler manifolds. And finally, this surprising result, we think that a very large class of ADS n equals 2 supersymmetric vacua are ruled out in 4, 5, and 6 dimensions. And this has some interesting implications for compactifications of type 2 and M theory. Thanks.
Hi. about the SU3 times SU3, there has been some ADS solution found by Zimpis and Lust, I think.
Yeah,
some time
that's
ago.
right. We wondered about this straight away as soon as we saw this result. In fact, Simples was in touch with us not long after the paper came out. Yeah, so what we concluded was that, so our statement is obviously strictly within 4-dimensional n equals 2 supergravity. And what we concluded is it's likely that one cannot consistently truncate the solutions that you find to 4 dimensions, perhaps. They're really 10-dimensional solutions somehow. But of course, because, yeah.
Okay, so it's about the dimensional reduction.
Yeah, I think that's what we believe. Right.
Bobby?
What about, is it useful for constructing n equals 0 solutions?
Yeah, I've been wondering that a lot.
One question that I was always interested in is, do there exist de Sitter vacua in n equals 2 supergravity in 4 dimensions?
Okay, the state of the art at the minute is that if you have n equals 2 supergravity in 4 dimensions with only hypermultiplets, you cannot have metastable de Sitter vacuum. This is a no-go theorem shown by Skruka, Louis, and another of their collaborators, Marta.
What's going on?
If you then include vector multiplets, I believe it's still an open question. Certainly with the case of non-abelian vector multiplets.
Oh, no, it's known that there's stable examples.
There are examples.
Yeah.
Okay. There we go.
Yeah. These were from 2004, right?
So these are the examples of Frey, Trajanti, and Frontline. Yeah, of course.
So, yeah.
Maybe Michel in this case, but can you construct chiral n+1 theories using this problem?
That's the big open question. There is a model of Ferrara and collaborators which uses one of their early constructions with very special matter content, and they claim to be able to construct a chiral spectrum. But I believe the masses of the mirror fermionic partners are fixed to be at the same scale, basically fixed to be at the electroweak scale at the minute, and therefore essentially already ruled out. However, I think there's at least many people that you talk to in the area will say that you simply can't have a chiral spectrum coming from an n equals 2. I think it's maybe still to be studied a little bit more.
But how do you give a mass to a chiral fermion without Higgsing the gauge group?
Exactly. I mean, there's Higgsing involved, yeah, for sure. I mean, I only know this one model where they kind of get a splitting between the two sets of fermions inside the Dirac fermion, and the two sets of Majoranas. So they managed to give a higher Majorana mass to 1/2 of the degrees of freedom in the n equals 2 Dirac fermion, but it certainly goes along with regular spontaneous symmetry breaking.
Final question?
Yeah. The fixing of moduli, you're saying it comes from the fact, I mean, it originates from n equals 2, or could it also be due to the specific embedding tensor values you got?
Absolutely nothing to do with the specific values. It's to do with the fact that you have asked for your n equals 1 theory to come from an n equals 2
Right.
theory. And it's very robust and very simple.
Okay, so that was this part of the session, and would like to thank all the speakers again.